This is section 3.7, modeling using variation. So solving variation problems. These are word problems. And ones like this. The daily profit P varies directly as the number of units sold in. If the profit is 4,131 when 810 units are sold, what is the profit when 520 units are sold? Your first step is going to be determine type. And type will be based upon some wording you see in here. Specifically, this says varies directly. So step one, determine the type. And you'll have one say directly. Sometimes there's another word besides direct. Sometimes it says, I don't know, just some other word that means the same thing as direct, where these two are connected. As this one increases, this one increases. That's direct. And that's of the form y is equal to kx. It may say inverse or inversely. I don't think there's any other words you'll see besides that. That's y is equal to k over x. There's joint variation, and it'll actually say the word joint. So this varies jointly with this and this. And I put x and z there, but you can have multiple items. And then a combo, which is a mix of the above. Now after that, then you want to pick variables that make sense. Typically, x, y, and z do not make sense in a problem. You choose P for profit, N for the number of units sold, P for profit. So those would be the variables here that make sense. Sometimes they give that to you, sometimes you have to pick them yourself. Step 3, look for the one example. Plug it into the equation from step 2 and solve for k. K is referred to as your constant of proportionality. And it's going to be the same no matter what problem, the numbers you plug in. Now, after you solve for k, then plug k into the equation from step 2. And then step 4, find what they really want. Okay, so if we look at this problem here. Step 1, determine the type. Daily profit P varies directly. It says directly. So directly is going to be of this form, y is equal to kx. So direct y is equal to kx. Step 2 says to pick variables that make sense. Now, where the varies is, that's where your equals goes. So this says P equals K. K never changes. Varies directly as the number of units sold in. So Kn. Then step 3, we need to look for a one example. You can't solve for K unless they give you one example. It says if the profit is 4,131, so P is 4,131, when 810 units are sold. So N is 810. So that's our one example. Sometimes it's in a sentence by itself. Sometimes it's like the first part of another sentence. Now we want to solve for K. So we divide both sides by 810. Then we want to plug that back into our equation from step 2. So we now know what K is. So P is equal to 4,131 over 810 times N. That's a new equation we're working with. Then find what they really want. It says, what is the profit? So what is P when only 520 units are sold? So P is going to equal to 4,131 over 810 times 520. So 4,131 divided by 810 times 520. So our profit be 2,652. Now problem number 2. The gravitational attraction A between two masses varies inversely as the square of the distance between them. So step 1 is to look for what type it is. It says inverse. And that's of the form y is equal to k over x. Now the inverse part is always the part goes down your denominator. So we'll look for letters that make sense. Gravitational attraction A between two masses varies as your equals. So we got A equals K is always up on top. Never have K in denominator. Inversely is the square of the distance between them. D for distance. Square means D squared, not square root. It had to say the square root for you to put square root. Step 3, look for one example. Force of attraction is 13.1 pounds. Okay, gravitational attraction is A, so 13.1 for the A. And when the masses are 10.2 feet apart. So 10.2 squared. Now we want to solve for K, so we multiply both sides by 10.2 squared. Then we get k is equal to that. Now, if you want to simplify that, you can, but you're going to plug it all in the calculator at the end anyway. So we then want to take that value of k and plug it into our equation from step 2. So we've got a is equal to 13.1 times 10.2 squared over d squared. And step 4, find what they really want. It says, what is the attraction? So what is A when the masses are 27.5 feet apart? So D is 27.5. So that A is equal to 13.1 times 10.2 squared over 27.5 squared. And I won't plug that in, but whatever that gives you when you plug in your calculator will be your answer. Problem number 3. Gravitational field F varies directly with mass m and inversely is the distance squared from the mass. It says direct and inverse. So this is a combo. Now there is no precise form for a combo. It's just however you read it is how you write it down. And specifically, when I'm writing it down, I'm going to replace my variables. So put my variables in there. Gravitational field F varies directly. So varies is your equals. So F equals. Directly with the mass m. So that'd be Km. K always goes up on top, never goes in the denominator. And the only part that ever goes in the denominator is the inverse part. So varies directly at mass m, and inverse is the distance squared from the mass. So d squared. Okay. Look for our one example. If a mass of 200, m is 200, and a distance of 5, so d is 5, give a gravitational field of 80. So F is 80. So that's our one example. We want to solve for K. Now 5 squared is 25. 200 divided by 25 gives us 8, so that's 8K. Divide both sides by 8, and you get K is equal to 10. And then plug that into this equation right here. So F is equal to 10m over d squared. And then find what they really want. What is the gravitational field? What is F? When the mass is 310. So you put 310 in for m. And the distance is 7. So put 7 in for d. Wherever that gives you, and plug in your calculator is your answer. Questions on these so far? I pulled this out of an old book. Well, I think all these I did. I got some math books from the late 1800s, early 1900s. So I pull them from different places. Do that for a reason. I'm putting this up on the internet, and you can't just steal somebody's work. So, but the copyright is expired on some of those. So this is pretty old. Weekly payroll P in dollars, a small factory varies jointly as the number N of men employed, number D of days that they work. When 30 men worked 5 days each, their payroll was $2,000. Find payroll when 42 men worked 2 days each. This is a long time ago. Well, I don't think there's any factory in the United States that doesn't have women working in it now. That's all men. And 30 guys worked a week, and the entire payroll for those 30 guys was $2,000. Gives you an idea of how long ago it was. Okay, step 1, determine type. Weekly payroll P in dollars in a small factory varies jointly. It says jointly. And that's of this form, y is equal to kxz. We want to pick variables that make sense. Weekly payroll P in dollars, so P for payroll. A small factor varies. Varies where your equals goes. So P equals K. Varies jointly is number N of men employed. So N for the number of men employed. And number D of days that they work. So D for days. Step 3, look for your one example. When 30 men, N is the number of men. When 30 men work 5 days each, so D is number of days. Payroll is 2,000. Now we want to use that to solve for K. So 30 times 5 is 150. Divide both sides by 150. Now, if you want to simplify that, you can. But since you're just going to plug it back into your calculator at the very end, then it doesn't much matter. We now know what K is, so we'll plug that into the equation from step 2. So P is equal to 2,000 over 150 ND. And then step 4, find what they really want. Find the payroll, so find P. When 42 men, so N is 42, work 2 days each. And that'll give you your answer. Now, number 5, many people claim that as they get older, time seems to pass more quickly. Suppose that the perceived length of a period of time is inversely proportional to your age. How long will a year seem to be when you're twice as old as you are now? This one doesn't have any numbers. This one does not follow that pattern I just gave you. This one you have to think more of what kind of factors are applied. It says, suppose that the perceived length of period of time is inversely proportional. So T for time is another word for your equals, inversely proportional to your age. So K over A for age. So that's a setup they give us. It says, how long will a year seem to be when you're twice as old as you are now? Well, twice as old means instead of A, you have 2A. So for example, if you're 20 for A, 2 times 20 would give us 40. So forth. Now your goal on these type of problems is get to look like the original, more or less. So I can factor a 1/2 out of that. and it more or less looks like the original, k over a. So the question is, how long will a year seem to be when you're twice as old as you are now? It'll seem to be half as long. Questions on variation at all? Okay. Well, that's into 3.7. And 4.1. Exponential functions. This is the national debt. I started back at Truman. Does anybody know who the first president was that got us into debt? George Washington. Very beginning, we were in debt. When you think about it, you're starting a brand new country. You're fighting a war with the British. You got to have money, right? I assume we owed it to the French, but I don't know for sure. There was one president that got us out of debt. Anybody know who that was? It was Jackson. Got in a $20 bill, I think. Um, he did it kind of strange. I think he paid it off with his own money, so it's not like he actually got us, you know, financially sound. But every other president been in debt on. But I started at Truman, and it's going up a little bit here, a little bit. Kennedy, Johnson, Nixon, Ford goes up, hits Carter, goes up, hits Reagan, really goes up significantly. Hits Bush Sr., keeps going up. Clinton about levels it off. If he had had another 4 years, you would have saw that actually go down under Clinton. Unreal what Clinton did in terms of the national debt. And then Bush Jr. took over, and you see it go up like that. Then Obama. And this last part is Trump, even though it's not showing it. And I don't even know. I haven't updated this for a couple of years, so it might really be up there with all the borrowing they've been doing. Now this is the nature of exponential growth. Grows slow, flies out of sight. A lot of people like to look at this and blame different presidents and so forth. They look at Obama, say, "Look at that, boy! Obama just really went on a wild shopping trip," and he didn't. That's the nature of exponential growth. It'll just keep growing like that, unless you do something to stop it. They look at Trump. If you don't like Trump, and you're sitting there, boy, look at how much money he's spending, and that's just the nature of exponential growth. When you start owing money and you start paying the interest really becomes high. My wife is a financial genius in our family, and I'm not. I'm a financial idiot. And I got in trouble with credit cards. Easy to do. And I think I was paying somewhere around $500 a month on the interest, not the principal, the interest. And it'd be like $5 or $10 toward the principal. So at that rate, I would have had to live to age 400 to pay it off. Well, she she manages our finances, and we're in sound shape now. So that interest is what really accumulates. If you look at this right here, Reagan is one that really got us into debt. I like Reagan. He had a good sense of humor, but and he had a pretty good religious side to him, but wasn't very good finance wise. He borrowed from Social Security in order to get the country in good shape again, because Carter had left it in kind of bad shape. There's no doubt about that. But he borrowed and destroyed Social Security in that. I had to take my dad to every political meeting during that time because he knew what they were doing. The idea of Social Security is you have this big pile of money that everybody pays into, and only the interest goes out to pay the retirees. So that pile of money keeps getting bigger and bigger, and as a consequence, the interest just becomes outrageous on what it accumulates. Works real well unless you borrow money from that fund. If you borrow money from that big pile of money, it doesn't accumulate interest. If you get a 401k at some point, some kind of retirement plan, you don't want to sit there and borrow money against it. It sounds like a really great idea. They feed it to you that way. Says, hey, I borrowed from yourself, and then you're paying yourself interest. You are, but the idea is that pile of money gets bigger and bigger, and it takes exponential growth. If you borrow from it, it screws it up. Bush Sr. is considered a bad president. I'm not sure if he was or he just got handed out a maxed out credit card from Reagan. Clinton did the unheard of. Like I said, another 4 years, he would have had that go down. Now, you could argue that what he did was bad because he cut military quite a bit. So maybe that's why we had all the problems after that. I won't argue that at all. Everybody paid more in taxes. I paid more into Clinton. So you have to do something dramatic in order to get it to stop exponential growth. Bush Jr., when he took over, he undid everything Clinton put in place, so then it continued its natural progression. If Clinton hadn't done his little number here, it would probably be almost a perfect exponential growth. And then Obama, a lot of people, these first ones here, they say, well, there you go, there's Obamacare. Well, Obamacare didn't take effect in his first years, so that had nothing to do with it. And he didn't really go on a big shopping spree either. Some people say wars. Bush Jr., here's Iraq, Afghanistan, so forth. Wars don't necessarily do that. Because if you look over here, we just got finished fighting World War II, Truman. And we're rebuilding all the countries and so forth. I'm not very good with history, but somewhere over here is Korea, Vietnam, not even little blips. Now, there is a difference between fighting a war where you're dropping $1 million bombs and just firing bullets, so there's a big difference there. But war by itself doesn't normally cause that. I like this graph. Now, I realize this demonstrates exponential growth, but there's more to how your country is doing than debt. For example, if I owe $10,000, is that good? Bad? If I owed it on my credit card, probably wouldn't be good. I'd pay pretty high interest and so forth. If Charles Koch, a billionaire in Wichita, owed $10,000, that's probably how much he blows in a month's time, right? So again, you have to look at a lot of other factors to see how your country is doing. So this doesn't say anything about what these presidents did in terms of the economy. I don't know. I'm not a business major. This just shows exponential growth. If you've never looked at one of those debt clocks, they're kind of fun. Scary, one of the two. Here's our national debt. And you can kind of watch it as it goes. Again, seems pretty wild. It's probably increasing. Just say the rate of change here. On how fast that's going, it's probably increasing $1 million every 20 seconds. So pretty good. Um, like I say, you'd have to be a business major to sit there and actually understand this to see, okay, that's really nice, but how's the country doing? I don't know. I couldn't tell you what most of those are. Interesting. That's in your pocket. State debt clocks. Let's see how Kansas is doing. I haven't never looked at this. Wow. Does that say we're $26 billion in debt? Doesn't seem like very good. But again, GDP is, I think, is a better measure of how you're doing. But that seems like a lot in debt. Debt per citizen. If each of us paid 9,063, we'd have our debt in Kansas paid off. Okay, let me look at population clocks. Where's the clock? That's not a very good one. Retrieve and data. Okay, so there's 7.8 billion people on Earth. It's a lot of people, and you see how much it's increasing here. Baby, 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 baby. Births today, birth this year, deaths today. Top 20 countries live. Shows you population growth. Understanding this is important because you need to make appropriate plans. One point in time, China um, was faced with the concept that their population was growing exponentially or going to grow exponentially, and they got worried. Back in the 80s, they instituted where you could only have one or two children. I don't remember which. You probably studied it and know the answer to that. And if you had more than that, they penalized you in some manner. Probably make you pay money, I'm assuming. So they had problems with, especially baby girls, were left in orphanages and so forth, because the farmers, the rural people, wanted to have sons that they could have worked the land, and daughters couldn't do that back then. And so they had that problem. That was a big thing back in the 80s, go adopt a Chinese girl. And they also opened up, not so controversial now, but was back in the 80s, they opened up state-run abortion clinics over in China because they want people to keep the population under control. Now, those seem like extreme measures, but when you're faced with your population growing exponentially, what do you do exactly? Hope for a pandemic that wipes out half your country. Um, eventually that'd be the only thing that will probably stop it. Wars don't normally get rid of that many people. Genocides do, but wars by themselves will not get rid of that many. Anyway, exponential growth. I think this one's a good one. So I'm trying to find one for the United States changing. You can see with the United States, it's changing slow, isn't it? They say Japan, their population, I think, is decreasing, and so they're facing shortages. So they'll bring in workers, I guess. But some of these other countries aren't. They're increasing exponentially, and eventually something happens. Your people starve to death. You'll have a plague of some sort, wipe people out. Wars, because if you run out of room in your country, you're going to invade, right? So it was back, I don't know, probably 7 or 8 years ago. Sure, none of you probably even paid attention because you don't live in Wichita. Well, some of you do in Wichita. But the news came out that Wichita was going to run out of water by 2018 or something like that. They get their water from, I think, Cheney Lake, and I think one more lake. But we're on a drought. The water's going way down, and they were saying we're going to run out of water. Well, that's kind of disturbing to me because I like taking showers, and drinking water is good too. Well, I think they were trying to get something passed, trying to get voters to vote a certain way. We didn't run out of water. So sometimes their science isn't quite correct. Sometimes they got political reasons behind it. But again, they have to plan this. If your population is growing exponentially, at some point in time, you're going to have issues. Okay. Now this section is mainly a calculator section, trying to get you to understand the nature of exponential growth. By the way, that exponential growth is a fantastic thing if it's your retirement plan. If you start retirement plan early, like in your 20s, early 20s, probably the best, then you'll find by the time you get ready to retire, you've got a pretty good amount of money that's accumulated. Because it grows slow, and flies out of sight. We're going to see that with these graphs. Okay, this one we'll approximate each number using a calculator. So 7 to the 3.1 power, I do 7 caret 3.1 and enter. Make sure you're out of graph mode, and that gives us our answer. Rounded 3 decimal places would be 416.681. Same instructions here, 9 to the power of square root of 3, so 9 caret square root of 3. And rounded 3 decimal places would give us 44.957. Now, if you have any trouble with any of these, then let me know. But otherwise, I'll go through them fairly fast because they're easy. Now, this next one involves E. E is like a number like pi. On your calculator, to get to E, the best one, there's 2 or 3 places where it's located at. The best one is second ln, and we'll talk about why. Now, I don't know what E is exactly. 2.7 is about all I remember, and then a bunch of decimal places. It is used to model growth, exponential growth specifically. So, e to the negative 2.5 power. I'll do my second button and then push the ln. ln is down here in the bottom left. When I do that, it puts an E caret in beginning parentheses. If you do second divide, I think it is, you just get E. It doesn't put the caret on there. Well, you almost always want to do the caret. And then I put in negative 2.5 and press enter. And round to 3 decimal places, our answer would be 0.082. Now this next problem is exponential function. Now what defines an exponential function is when you got a variable in the exponent. Now the instructions here are to graph this, so I'll press my y equals. And fix my calculator from yesterday. Okay, now y equals clear. And I do 4 caret x and then graph. Now it looks like the graph just stops here. It doesn't. It keeps going forever this way. It just got so close to it, it looks like it's 1 with it. That's an asymptote, actually. Your graph's growing slow, growing slow, growing slow, and then flies out of sight. This is what happens with retirement plans if you start early on. If you start in your 20s, grow slow, hits retirement, flies out of sight. So, in retirement, you're going to Hawaii, you're going to Montana, having trips like that, going over to Europe, so forth, versus greeting people at Walmart. So I cannot emphasize that enough. I had somebody that after this, I told them, I said, go talk to somebody at the bank. They'll give you the real numbers. They went and they signed up in their early 20s for a retirement plan because they saw what would happen if they invested all their lives. My wife started us at age 35, which is too late. I'd probably have to work to age 80 before I see it fly out of sight. To give you a kind of an idea of exponential growth, how it builds, and I'm just going to do this just based upon one deposit of $1,000. Say I have $1,000 I want to deposit. And so let's see, let's say 2%. It's not very much, but my wife and me had our biggest fight over finances. Huge fight. I was in the wrong, but she was. I handled it very poor. Or I was correct, but I handled it very poorly. I was in the wrong. She went to the financial planner and asked me if I wanted to go first. It's like, no, I think I'd rather use the Japanese suicide sword before we go listen to somebody talk about finance. I don't find it very exciting. No offense to people into business. That's where you plan to major. You probably think the same thing about math. But she came home all excited. She said, David, I have fantastic news. We're going to be putting in $1,000 over this year, and at the end of the year, we're going to have $2,000. We'll double our money. And I can't help it. I get sarcastic, nastiness comes out of my mouth, and I said, well, we need to go find a different financial planner. She said, well, what do you mean? I said, we need to find somebody that doesn't deal in drugs. So I said, that's the only way you can double your money in 1 year's time. At the conservative level we are. We're not the high risk stock people. And a big fight. I was right, but I was very wrong. I could have said it lovingly. I could have said, honey, I think you might have those numbers wrong. You might want to check with them and so forth before you tell too many other people you're going to double your money. Now here is a 2%, which isn't very good rate of return, but we'll go with that. And you see after 1 year's time, we've got an extra $20. It's like, wow, we can go eat at McDonald's. After 2 years, it goes like this. Now this is just a one-time deposit, so hers is different. We're gonna put money in each month, but still, you just can't see that rate of return in 1 year's time. So you see it's growing a little bit. After 12 years, I got $271 that I've saved. It's like, wow, big deal. After 50 years, it's up there. Okay. Now I like the numbers start growing. After 500 years, we're at this, whatever that is. So after 500 years, my $1,000 deposit is now grown to $22 million. This shows you that if, like the retirement plans or Social Security, if you had that big pile of money that kept growing, even if you just put an initial amount in, after a period of time, it just grows exponentially. Now, if I put 5,000 years in here, $26 gazillion. I don't know what that is. So after 5,000 years, my original $1,000, I now can buy the entire planet. Again, this just shows you the exponential growth. That was always my dream. Put $1,000 in a bank account, pass it from generation to generation, and at some point in time, the Hayes family owns the planet because of the exponential growth. Now that won't happen, of course. Banks only let you accumulate so much, and you have to have activity in your account. And at some point in time, your family line is going to fall away. You won't have children, whatever. So, but that shows you what happens with exponential growth. This is why if you're going to medicine, they will give you like strong medicines in the hospital to knock back exponential growth. Because if you got little bacteria or viruses or whatever grow in your body exponentially, at some point in time they'll grow like that and they'll kill you. So they have to do something dramatic. That was their big worry on the pandemic, is that it would be exponential growth. Because if it grows exponentially, then at some point in time, you have a huge amount of people that are passing away. Okay. Anyway, that's our graph. Just keep in mind, this keeps going forever this way. This one, we got 1/4 to the x power. So press my y equals clear. Beginning parentheses, 1 divided by 4. Closing parentheses, caret x. Then press graph. I'm just entering exactly as I see it. Now the 1/4, since this is less than 1, flips it around the other way, but it's still going the same way. But now it drops dramatically and then levels off. So the nature of it is different, but still an exponential growth or decay. Now in this problem, the graph of an exponential function is given. Select the function for each graph from the following options. We're trying to match the graph to the function. Now if I graph g of x, that's my basic function. So if I press y equals clear, you get bored with these graphs as they look all the same. Because that's the nature of exponential growth. Isn't because Republicans or Democrats spend a lot of money in our national debt, that's just the way it grows. So it looks like this. Looks like it passes through 1. Well, as I look at this right here, these numbers in here are shifts. If you remember those from before, When a number's inside with the x, in this case inside the exponent, that's going to shift it left to right. So it's -1 make us think left 1, so it's really being shifted right 1. And that actually is the answer. Because it does look like that's been shifted right 1. Now a -5 to the x, that flips it upside down. So I know it can't be h, can't be I, and can't be k. And a +1 at the end, that shifts it up 1. And if this is passing through 1, then shifting it up 1, it would pass through 2. So the answer here would be f of x. Now this one says, describe the transformation occurring, graph each function. The +3 shifts up 3, the -1 here shifts right 1. So this would be my basic graph, shifted right 1, up 3. If I graph this, I got 4 caret. The key to it is if you have more than a single variable in your exponent, put parentheses around it. So we'll put parentheses around the exponent, x minus 1, close parentheses, and then +3. Now it was right along the x-axis here. You see it's been shifted up 3, and it's also been shifted right 1. But again, shows you the nature of exponential growth. Grow slow, eventually flies out of sight. E to the x minus 2. Second ln to get the e, and it puts a caret, puts a beginning parentheses. So all I have to put in is x minus 2, and then graph. Again, grow slow, flies out of sight. Every one of these is looking the same, aren't they? That's just exponential growth. Now this one will be flipped upside down because of the negative, but let's go look at the graph of this. So negative e, so second ln, x plus 4, close parentheses, minus 1, and then graph. Now here, it's dropping slowly, and drops dramatically then. You know, and you see some of these in, well, a lot of this is in medicine. So if you plan to go into nursing or be a doctor or something, exponential growth occurs quite a bit. Obviously business. Don't forget the midterm, last call. I'll be in my office today from 1:30 to 4:30. Today's the last day you can take it, or if you're at a distance, you arrange a proctor to administer it to you. So if I don't receive that today, then you'll receive a 0 on the midterm. I know people are anxious to see what in the world they got on it, but I can't pass back until everybody gets done taking it. So that'll be today. We just finished chapter 3, so we're ready for another test. So today is the 14th. So a week from today is 21st. So it's out there now. I'll go ahead and put it out in the other section, the Wichita section also. So again, you can start taking that, so forth. We'll go ahead and stop there. We finished 4.1. Questions, anything? Well, have a good day. If you're taking the PSAT today, good luck. So I've heard from quite a few people that they're having it today. If not now, maybe it's, I don't know.